Hello, welcome to the second streaming session this year. Last Friday we started afresh by kind of like showing off the GRiSP 2 board sample I have here, explaining all the little bits and pieces. So there's a video. If you missed this, you can actually watch the video. You can go to the Twitch channel, highlight, but it will also, I think it's already on YouTube, but maybe I can actually check the link and paste you the link afterwards. But it's on Twitch also as highlight video. So there you can actually see all the parts of GRiSP 2. So we won't do this today again. Today will be exciting because, at least for me, I'm kind of like trying out a new thing we're building. Actually, a thing we're building for a while. It's about PLCs and PLC languages and an IDE for these PLC languages, which is built with Erlang and basically a JavaScript front end, a web front end, and it's compiling to Erlang. And I want to show you a little bit of this and also kind of like make this work on the GRiSP board, because we've worked kind of offline on a laptop for a while. And now we really want to have like real actuators and real sensors for a demo we will be giving in San Francisco in about a week. So there is CodeBeam in San Francisco, where Barbara and I will be speaking, and we will be speaking about this stuff. So I thought maybe I work on a demo a bit while I'm streaming. The thing is, like, I did not prepare for this. So I did not touch the application for a while. We will install this and try it out. Barbara and Miriam, who have been working on this for in the last, like Barbara for quite some time and Miriam since like a few weeks, are hopefully in the chat and watching. So if I stumble, I hope they can help me. So the plan is to show you this IDE we are building, which has a very nice auto layout algorithm built in, which is starting to look good. And then, hi Miriam. So at least one of them is in the chat. I'm not alone. So show you what we've built so far, basically on my main computer. And there's Barbara. Hi. So actually, we should start to co-stream. That kind of like that is fun, but I did not figure out the technology for that, for co-streaming. And when this works, I want to hook it up to a GRiSP board. So we need to install, make a distributed application on the GRiSP board, which will be a nice rehearsal of actually how to get a distributed GRiSP board running. And then we try to kind of like move part of the application to the GRiSP board and then make the actual LED blink. So if I kind of like listen to my own list, we probably won't make it today. But yeah, let's see how far we can get. So I promise you will learn something about PLC. Well, first of all, what is a PLC? PLC is the acronym means Programmable Logic Controller, and it's a name for the computers that get everything like working, all the machinery, from the garage door opener, like to like the barrier when you go out of a larger parking garage, to whole factories, conveyor belt lines, factory automation stuff. That's all done with PLCs. All the control stuff, which needs to be custom, is done with PLCs usually. And nowadays, PLCs are pretty beefy, like embedded PCs. Like they have quad cores and all kinds of things, but they used to be much smaller, and they have quite some history. And they have their own kind of programming languages and their own group of programmers, so-called PLC programmers, which know very well how to get everything running. and who know these obscure PLC programming languages, which you will see a bit today, I hope. At least if I can manage to get this running. So let's get started. I will explain the rest of the stuff while we go along. Desktop dual cam. Here you see a GRiSP2 board, by the way. Put it in the picture. It's a nice placeholder. Let's adjust the camera a bit so it actually points to the table only. So yeah, that's the cable of the camera. Yeah, good. So we start with a shell. And I'm going into my Twitch folder. Yeah, let's make a subfolder PLC stuff. And then I'll try to clone. Actually, where is it? I prepared this. The URL. So actually, is this a secret? No, it's not a secret. I mean, you can't clone it because it's on our private Bitbucket. So no worries there. That's our current demo. Oops. What? Oh, double HG clone, because I cut and pasted the clone already. That was an easy one. Good morning, T-Trev. Nice to see you back. Okay. 18 change sets. So now we have this PLC with Ampel. Ampel is the German word for traffic light, by the way, which kind of like was nicer than traffic light. And it's the traffic light, like the controller for traffic light with sensors. So let's try this out. I did not do this in a while, so it's supposed to actually pull all the other stuff in. Yeah, I know. Warning, warning. Plugins. Yeah. That's all normal. We have PLC fake I/O, which we want to replace with PLC real I/O for GRiSP boards. Which we need to show this up in San Francisco. So I thought, like, on today's Twitch, I'll work on that. So again, doing real work, like with the whole control system stuff. So what we are pulling here in, I can actually talk a little bit about the dependency. Ampel, that's the traffic light, that's the actual application. And this application is partly written in structured text, which is one of the syntaxes of the text syntaxes from programming languages. Structured text looks a bit like Pascal, but it has a lot of like added stuff to it for control systems like data types for time and all kinds of other things. And the standard we are implementing is actually IEC 64099. So these PLC languages come in different flavors. There is one standardized language which is used since quite long already and which is quite entrenched, which is IEC 61131, which is normal PLC stuff, except basically there's a German company who dominates the European market, who has their own language, which is very similar but different. And IEC 64099 is a new language, and new in PLC world means it's only 15 years old, or actually a little bit more, I think, by now, because I'm saying it's 15 years old since 5 years and kind of like 5 years passed. So it's probably 20 years old. And it is an extension to the normal PLC languages for distributed systems and for event-driven programming. So one thing one has to know, like normal PLC languages work in a way that you write your program, and it has kind of like a data flow paradigm. You have data flowing through the system. There's also graphical representations for that, and This data flow is implemented as synchronous data flow, and the concrete implementation is that the whole thing creates one big loop which runs in a loop. And that's your cycle time. And the cycle time is basically twice the cycle time is your real-time reaction time, your maximum latency. So the way this is, it's very easy to understand. You don't model your real-time stuff. You build your program, you run it on a PLC. If your cycle time is too large for your application, you buy a larger PLC. Easy. So that's, and this plugin is basically the plugin for the compiler for this language, for structured text. So we have a compiler from structured text to Beam, or actually to core Erlang. If I have time, I tell a little bit about core Erlang maybe later on. Kind of like get the impression that I will be so distracted by all kinds of other topics that we won't get to the actual GRiSP stuff. Well, I try to hurry up. So yeah, it compiles a Reaper plugin. That's the compiler. And then it wants the runtime for it. So there's a runtime for it. That's the PLC fake I/O. That's kind of like a way to fake I/O on a like fake like digital sensors and actuators. And that's the visualization stuff, and which then needs Cowboy as a web server. And we also use GPROC to actually do stuff. Oh, failed to fetch and copy dep GPROC 0.8.0. Okay. So we're depending on a pretty old so it's also some warning was like OpenSSL, and we don't need OpenSSL. Unable to load crypto library. Now the fun starts. Did I build my Erlang 21 without crypto? That would be stupid. Image not found. But it's actually crypto ISO from users pair Erlang 21 lib crypto. But there is a shared object. Failed to load NIF library. Image not found. OpenSSL might not be installed on this system. I don't believe this. But let me check in a little offline windows. Well, I have an OpenSSL minus version. So why is this not, why do I have this problem now suddenly? Do I have the wrong version maybe? How do you get the version? 1.1.1d. September 2019. That looks okay. And why did it? Why does this have anything to do with fetching GPROC? So okay, this is interesting. Well, it's actually too interesting. So it's actually the fetching Cowboy from Git. So that's the first Git dependency, and that already breaks, and I have no idea why. This is annoying. So maybe I got some to. I mean, I didn't upgrade anything, and everything worked fine on my machine. Well, let me check. What do we have? Crypto start. Okay. This is quite weird. Opt local bin open SSL. Anybody any idea? Let me see. So libcrypto is an opt local lib, and it's there. And why is it suddenly broken? I mean, this is really weird. No. Well, apparently I can't do anything because my rebar is broken, because it can't load, suddenly can't load crypto. So this is a new experience for me. Yeah, maybe we need to set up basically a version for gproc, as we do for Cowboy. Yeah, but it's not that it can't find gproc. The problem is it can't load crypto, which it needs to do. That's the first time it needs to do HTTPS loading, and then it wants crypto for that, and it can't load crypto. So my normal Erlang can't start crypto. But it wants libcrypto library not loaded. Opt local libcrypto 1.0.0. Dynamic library. Or maybe I'm missing the, I have an idea. Local libcrypto. So apparently I broke my machine, because now I have 1.1 and it actually, this Erlang actually looks for 1.0. Okay. Well. That's not. So actually, do I need Erlang 21 or 22 for this? Um, what is everybody else using? Erlang 21 or Erlang 22? Okay, should be working with both. So I have 121.0. Well, um, build release 21 point or list releases, and let's build 21.1 because I assume that I'm I updated my OpenSSL and my 21 is broken. And actually, I can't remember when I did this, but apparently I did not pull anything with Rebar 3. So this is going a very unexpected way. We'll see. In the meantime, we can actually work on making a new GRiSP application while this builds. So Rema 3, new GRiSP app, name equals PLC demo. Yep. Test equals volumes GRiSP. So we make a new PLC app, PLC demo app. Pilot. Ooh, what? So I really broke it. I really broke it. I can't even build a GRiSP app anymore. So this used to work. Probably I should have used my laptop. So what is curl doing? Building Erlang OTP. Yeah, I'm sorry. On this machine, I did not write any Erlang code for at least 2 weeks, I think. So no Java compiler found, which is weird because it asked me, yeah, I don't care. I don't need all this. Oh, it's downloaded only, it's building now, okay. I see. Yeah, in the meantime, I can actually, I can try to explain you a little bit, but without possibility to show you the code. It's kind of like hard to explain how this looks, but maybe I can pull up some image. Let me see, where did I get an image while this builds? To show you how this looks. So that's how a 64099 PLC application looks. Check. There's my window. Oh. Yeah, Barbara just told me on the back channel she can send me images. Yes, please, Barbara, do so, because then we can have something to look at. So I make this a little bit larger. So that's actually the traffic light application. So what you see here is, I explain you the outside first, while curl builds my OTP here. You have these boxes, and each box is a so-called function block. That's the unit of processing in a PLC language. And these special kind of function blocks for 64099, they have this like head and body. I hope you can see my mouse. It's kind of like on the picture, it's not so large. So the upper part and the lower part. Normal function blocks don't have this, but these have it. And kind of like there's inputs and outputs, which are, you see with the named labels. So let me just zoom in on one. Oops, sorry. Let me show you one in large. So that's basically the whole AMPO controller. So on the left side, there's inputs. On the right side, there's outputs. And these are connected to each other, and the inputs and outputs in the head, in the top level, are events, and this is data. That's kind of like the difference to the old PLC stuff. So now we have events. So If an event is not happening, event is like a singular point in time. If an event is not triggered, nothing happens. And also basically the data is only read, only valid if the event triggers basically. So, and here we have basically an event go, which is kind of like, yeah, go. Then set yield, that's kind of like the event that we use from here, from the sensor. That's a sensor which let's assume this is a road sensor. It's actually an inductive closeness sensor which we use in the initial demo. And if basically the sensor has two event outputs up and down, which means it's triggered or not triggered, and then there's a value which is here undefined because this is not running yet, and it's only a picture, and that's the yield value, which means like you're supposed to yield to the other side. So the traffic light 2, A2, that's the name, is yielding to sensor 1. And then you have like times parameters that you can input there, like the yellow time and the green time. And then you have a delay, and then you have these wires going places. So let me show you a different picture now. Or maybe let's check in on our, no, it's still building. It's kind of boring. Let's look inside such a traffic light. Barbara pasted me another picture. 1 second, downloading it. So that's actually how the IDE would look. That's kind of like lame that we show this as pictures. Why we actually wanted to show it live. So that's how the IDE will look. This is done for Bosch. So they have their little logo there. So thank you for Bosch. That's how the source code looks. That's one function block here. And you have like little extra wires here, which means which event is connected to which in outputs. And then you have this little diagram here, or that's the state machine that's hidden there. So let's have a look. Let's zoom in a bit. So that's how structured text looks. You have basically keywords, function block ample, which is the name of the function block. And then you have input events, which is basically the lines going in. And there you have this width. That's kind of like the data input that this is connected to. So this data value is only valid when this event triggers. And then we have the output, which is also connected. Basically, when the set event triggers, basically the red, yellow, and green value is valid. And that's the normal input and output values, basically. And then you can have like internal variables, which you don't have here. And what we have here is basically that's defining the state machine. So every function block has a state machine description language defining the state machine. So you basically define the states. Like there's one state called ini, which is the first state. It ends up in this ini state. And then there's always the state name here in front. That's the number of states. And then after the colon, a list of algorithms. I show you algorithms soon. That's pieces of code which are run when this event triggers, or when we enter this state, then this algorithm runs. And the thing after the arrow is that's the event that triggers when we go into the state after the algorithm runs. So if you enter a state, first the algorithm runs, then the event triggers. And you can see we can have like multiple algorithms and events. But what we have here is basically we run this algorithm and then trigger the set event. And then we run a zero algorithm and then we trigger the other event. So that's describing what happens when when the states are entered. And in some states, nothing happens. Can yield, nothing happens. And then for a state machine, you need transition. So that's the transition from state ini to state RRR ST. That's one that's always true. That means basically when we boot up, then this is always triggered, and then we plunge into this state, which is basically the whole reason for doing this is that this algorithm is run once and the outputs are set. And then from RRR ST to RYST, we go when the go event triggers. So go is an input event. If you look at here, event input, go. So when this event happens, the state transition happens. Likewise here, so actually we need to make sure the keywords actually, here you see the keyword things. On line 32, the question is, I automate things, is set and the other trigger synchronous? Set and, no. Yeah, well, you can, it's allowed. But if there would be another algorithm here, like before the other, if there would be an algorithm, it would first run this algorithm, then trigger set, then run the other algorithm, and then trigger other. So the way we implement it is we trigger it one after the other. Because actually two events are not happen at the same time. That's the definition of events. Events are discrete and separate. Every event is separate. So we first trigger set and then other. So they're kind of synchronous, but not quite. Yeah, Barbara kind of like saw the formatting issue here. Like the small 2 doesn't trigger, but the language is case insensitive because it's like Pascal. So we need to be careful about that. I mean, I don't like case insensitive languages, but that's how it's specified in the standard. So what we have here is basically, that's a more complicated one. Like from can yield to YST, we have something like in the square brackets, which is a condition containing variables. And you can have like combinations of like events and conditions. Like when this event kind of came in and this condition is true, then you do the state transition. So it's actually a pretty rich state transition thing. And let's look at the drawing here. That's basically that's how we plot the state transition. So ini always goes to this state, and then go gets us in this state, and then next gets us in this state, and then next again gets us in this state, and then this by itself, basically, we plunge into the next state and run this algorithm. Actually, what does this mean by itself? Let me see. That's can yield goes where? What's the transition of can yield? So can yield to YST would be actually on condition yield equals 1. I think we found a drawing bug here, because this condition should be named here in the square brackets. That's missing here. So we should see the condition here, and then you go around, and so basically it plunges into this, and then it goes around and around, like it's supposed to be for a proper traffic light. And the algorithms are drawn on the side, so that's the algorithm, and that's the event that are triggered. Like if you enter this state, our Y algorithm is triggered, and the set event is triggered, and then the wait event is triggered. And then we go in the next state. And then the green algorithm is triggered, set and wait, etc., etc., etc. So that's how it works together. And you see traffic light, there's RY, red and yellow. Then there's green and yellow and just red. So that looks curious. So let's look at the algorithms. So there's a section, oops. That's cut off. I can't show the algorithms, where we basically set the red, yellow. You can see the source code here. Red equals 1, yellow equals 0, green equals 0. That's the red algorithm. So we set this, and then we trigger the event, and then the respective lights go on. So the other algorithms are likewise. Yeah, the first one is actually not missing because it's empty. So from the transition basically from ini, oh yeah, it's just 1. It should say 1, or so there the empty would not be, I wouldn't mind, but yeah. So let me get you another image. So that's the inner thing. And then we have another example. Actually, what's my compile doing? Oh yeah, we have a new Erlang. So we need to install it. Oops. Didn't want to split this. Install, how does this work? Build 21.1, and we want to have this in home / Erlang 21.1. So installing already. Let me see what I else can show you. I can show you this in the thing, but let me show you the overall drawing again, so we can actually see get the big picture of the traffic light. Let me get you the other picture again. Download this. Where's my image? Check. So that's the overall thing. So the algorithm or the implementation we looked at is basically this sample thing, this block. And this block, there's a delay, which is basically a delay line. You can basically configure the value here, and it like this event comes in, and then it waits for a while, and then this output event is triggered. There's an initialization delay, which you sometimes need because you want to initialize some things early. So you trigger an init event to kick this whole thing off, and then after this has been done, you want to trigger the next thing because you don't want to do things at the same time. So this is Go, that gets it starting. And then there's set yield, which is kind of like wired up to this sensor. And then if you look at this next event, so next actually drives the state machine around. Like this comes from this delay, and this delay gets its input from wait. So whenever wait output is triggered, we go through the delay, and then we get our input event again. So that's kind of like what drives the timing of the whole thing. And then there's this configurable values here. And then there's the outputs red, yellow, and green, which is driven by the output. And the delay is actually also an output because that's a value, and the interval is kind of like triggered by the algorithm. So we set the delay to a certain value. And that's how this traffic light works. And then it goes to these MIO out things. That's basically red, green, and yellow. That's basically just one LED on this old hardware where we did this running. And we have two instances of this function block, which is the two roads basically crossing. And they talk to each other. So they say yield, which means that you are allowed to actually go green. So and the way it does it basically when there's no traffic, no sensor, then basically one traffic light stays green, the last one stays green. And then when the sensor on the other line triggers, then the other traffic light gets kicked, and then it tells basically, well, actually the traffic light that has the sensor has not the sensor, gets triggered yield, which means give away give the right of way to the other traffic light, and then the other traffic light can go through the sequence to go green. And then this stays green. And if there's traffic on both sides, they do the normal traffic light thing. Okay, I think our Erlang should be installed now. So now we need to activate this. And then we see if crypto is still is working again. So now we have L 21.1. Crypto start. Much better. Okay, we have a working Erlang again. We just need to remember to activate 21.1 everywhere. So we do this here immediately. And then our rebar 3 compile should actually work much better. Progress. Well, that's what twitching is. You see how the sausage gets made, what happens in the daily life with the tools. That's a bunch of warnings, deprecated stuff. We probably need to do something. And if I do rebar 3 shell, this should actually start this whole thing up, which looks good. That's the expected stuff. So there's events happening on the function blocks, and this is supposed. Ooh, failed to boot PLC with for reason bad return. Well, PLC with up start normal exit bad match. Error other in use. Haha. Oh boy. I have another thing running on this port. Does this mean? Ooh, that's not nice. Which is it? Which server is running on this? It's not Grafana. Lovely reports, yeah. That's old style reports here. Info report, yeah. Kind of like old school. So the thing is, this is supposed to listen on port 8080, but I seem to have something else running on port 8080, but I forgot about it. I have no idea what's running on port 8080. No. I need to remember the command. Let's start minus PTCP, I think it is. And all, or probably all. Minus A. So that's all the connected things. So that's localhost listen. So I assume that something is listening on 8080, and it should actually show up here. But actually it's not showing up here. What's going on here? We have a bunch of things open, probably by my browser. That's 8086, which is connection to a GRiSP board. There's more stuff to come. I was not patient enough. That's the open port. Now you see all my open ports. No need to try those. It's still not done. So we have connections to a GRiSP board. GRiSP 200 is actually, that's actually the GRiSP board that controls my solar heating control here. So you see the open ports here. EPMD is there, but I kind of like miss 8080. Barbara, is it really 8080 or do we? No, there's more coming. Now I got all, but I don't see 8080 here. Well, I mean, 8080 is probably a website, so why not? No, that's not a browser. Sorry. New window. Let's see what's going on localhost 8080. Maybe I can figure it out. Oh, I have another PLC application running from ages ago. This is a super old one. Oh, that's funny with quotes. So how do I find those? Oh boy. So one of those needs to be so that's a solar heating controller. PLC demo, huh? No, that's my new one. But that's a new one. Oops. I don't want you to see this. I have to kind of like go into top secret for a while. I show you my table. So I can switch my screen to the secret one, and there nothing is running. Let's close this. So which one is rebar shell? That's the one. Ah, I got it. I found it. Okay. Okay, I'm back. So let's test. So this should not work anymore. And this was super old. Yeah, can't connect the server. So that looks much better. Let's just quit this and restart it. Yes, I want this. This is a web server. So now it seems to work. And now I go to localhost 8080. And it looks very similar, but it has a much newer version behind it, basically. That's kind of like weeks ago I tried this. So we have several ample apps here. And there's two things. There's live mode and edit application. And I think I go into edit application first. Doesn't work. Help. So I'm probably on the wrong page. On the applications page. But these, I probably didn't click properly. I don't know what happened. So yeah, this is Erlang serving this picture. And actually this layout you see here, this is calculated in Erlang from the source code. So we have the source code of all these connections. That's how these connections look in source code. And to, yeah, I kind of like the button worked. So to show you that this actually works, or that this is actually not fake, let's delete a few connections here. So this is an editor here, so we can actually delete connections. No? How do I delete? Cut? No. I'm in live mode. Oh, I'm on live mode. I can't edit here. So now I'm in edit mode. So that's the edit mode. It looks a bit different. Color is different, which is good. So I need to stop first. Really? I should be able to edit. So now I can delete stuff. And what happens, like after 10-second pause, the compiler runs again, and then we should see the updated thing without a few connections, except we see the same one. Do I need to reload? Oh, but then it's still there. Maybe I need to really stop first. So let's go to live mode, stop the app. And now I'm allowed to edit. Stopping is the same as going to edit mode. So I stop the app, I delete something, then it's supposed to compile, and then we are supposed to kind of like that a few lines here disappear. Except, oh, I need to click to start. Yeah, you see? Layout changed, different layout. I thought this updates by itself. I saw this. So let's remove even more. Like, I was impatient. Yeah, now you see these connections are gone. It's only the values connected, so it's getting more and more disconnected. So then if you click on these things, then you see the state machine. Oh, the state machine looks different. we can make it after compile. Why is the state machine looking like this? Now I clicked on something that doesn't have ST code, doesn't have a state machine. Well, this looked differently in the picture I got. But it's still the same thing. It's basically the algorithm dangling off this, and you see the small thing here, but something is probably out of balance here at the moment. And you can also see if I add another transition, let's say I go from R_st to G_st when we get the so now we get a syntax error because I'm not done typing. Now we get, let's say, also with the go. No, that's not good. Different. Next. So I'm adding another thing here. And you see, the state machine immediately updated, except that it's not drawn like this for me. So something's not working at me correctly. There's also, you can zoom this, and there's also this logo up there. So yeah, that's kind of like the IDE that we are in the as you see, we are in the way of building. So you can actually edit this stuff, and then let's go. How do I get out? Ample up here. This works. And there's also like function blocks which are look like this. That's function block mio in. That's mio is the name of the I/O board that we were doing this, and you have basically all the inputs and outputs. And then basically algorithm mio in underscore callback in Erlang, which means it's looking actually for a module this name, which is an Erlang implementation of the innards of a function block. So we can immediately create the Erlang version. And in the final application, what's supposed to be that you can actually, so actually that works also nice. You can actually hover over lines and you see where they go, which is helpful. And probably the grid in the back is for our own orientation, because we're still tweaking this algorithm here. But it's already looking quite good. We don't have, I think this got some improvements I didn't see yet, because this is pretty good. So maybe let me tell you a little bit about, if I reload, do I get the old source code? So I'm restarting up, so I get the old source code again. So I can actually look at this. I can show you how this is running. Error in graph creation, bad edge. Interested. I think I found a thing. Yeah, let's ignore this. We have this, no, not fake data. Is it fake IO? No. Mio fake? Was it really fake data that, let me check. Mio fake set sensor 1. Okay, I'm actually copying this from the chat. So what we do is, at the moment, nothing is happening because all the sensors are inactive, and we kind of like trigger both sensors active. So then you see immediately stuff is happening. And then the other sensor active, which is a fake sensor, kind of like, and now you see this is actually running. And now if you look at what's happening here, Let me zoom in a bit for you. Oh. So here you see what's happening. You see the out. Can you see this? I hope. Oops. How is my touchpad? This zooming is not perfect yet. So you see how the traffic light kind of like goes from like red, and now yeah, red and yellow, and then green, and those values kind of like get also changed here. So we had a version where we actually flash this up when stuff is happening. We are working on that. I mean, we still have time until the conference. So looking at the clock, I think that's almost all I can do today. So there's no running this on a GRiSP board because we already took an hour, and I have to kind of like finish on time because there's a lot of other things to do. So the plan now is this Mio out is actually for this hardware boards. Let me show you. There's these hardware boards which had then this Mio board which was connected here, and that's kind of like a predecessor to a GRiSP board that runs GRiSP software stack, and it runs a vanilla one now, but it was for industrial I/O. So do you see this, like these industrial connectors? That's industrial Ethernet connectors, the round things here, and that's the power connector, and that actually was done for Bosch Rexroth years ago. And now we want to replace it basically for the demo. I had a demo like also years ago with like little traffic lights, but we want to just use the LEDs on the GRiSP board and run it on vanilla GRiSP boards, which also run it wirelessly, because here we needed a network. And for that, basically, we need to replace this Mio code. Maybe let me show you a little bit of code. Let's dig in a little bit in the code. So what should we do? I think I need an editor for that. I need my sturdy MX. Options, set default font, kind of like 14, maybe a little bit more. Options, set default font, 24. Oh, that's too large. Options, set default font. I think we stay with 18. And then we size it to our window. Okay. It's really thin. I don't like this font. Options, set default font. Let's go for 14 after all. That looks better. I think it's readable. It's supposed to be readable. So we scale this up. And now let's see where we find the source code. So this is just my GRiSP app. No, that's actually another one. I'm in the wrong directory. Sorry. So here's the local PLC with sample. There's like, that's just the top level source code, config. So we need to go into the build directory, default. We don't want the plugin now. So let's have a look at fake IO. So that's showing us how we can actually implement what we actually plan to do. So we have this Mio in, Mio out, and its callback thing. So if you look at this, that's the, let me see, can you see this correctly? Yeah, I think so. So that's the Mio in structured text, and it basically says this points to this callback module in Erlang. And so there's Mio in callback Erlang, and that's the Erlang implementation of the callback. So it's behavior PLC function block. That's the behavior that kind of like you need to implement. and there is a handle in event, handle info, handle info. So that's basically all that is. There's handle in event. That's an event comes in, and you need to know that basically the event together with the data that's connected with. So if I show you this again, we stop the app again, and let's click on this, and then zoom in here. So basically the event here with the connected data, this each of these groups, each of these vertical bars get actually mapped into a message, which is sent between function blocks. So every function block is actually a process in Erlang, which is very convenient. So we have concurrency. We just use Erlang's concurrency. We don't do any fancy stuff. This is very easy to implement. What's that out comment and out code? Interesting. So I think that was some debounce code I started, because the MioIn has basically is now greatly simplified. There was a more complicated one in the past. Gets a handle in event, and that's the name of the event. That's the init event. So the init event comes in. That's the only event that MioIn has. Let me show you. So MioIn is the sensor. It's a sensor, and it looks like this. That's MioIn, and the only event it has is this init event here, and which is connected with channel, interval, and debounce, which is the parameters. So which input channel do you want? What's your debounce interval? Or in which interval do you want to read? And debounce means a kind of like majority election for so many measurements to do this, because when you have like inputs where you could actually connect switches, then they could bounce, and that would actually then trigger multiple events. So you need a debounce at the input, which kind of like tries to not be very jerky at every little interval. So I can show you. I think that's picture's better. Debounce. Debounce probably should show me. Yeah. Like for example, that's a scope picture. The one that's how it looks on the wire if you switch on a switch. So you get all these little jiggly things, and then it stays on. So what you need to get rid of is these jiggly things, because it would trigger a lot of events which do nothing. And that's what debounce is for. But I have the suspicion that this is not actually, this is an old application about it. I don't know. Oh, that's already fake I/O. Interesting. Oh, that's already the fake one. So basically it's an implementation of MioIn callback that's actually hooked up to the fake. So the thing is, we get the event in it, and then we get variables in, which is our record. So this record contains all the variables, and we need to make sure that this matches what the ST code does. So we have variables, channel, interval, debounce. Debounce is set to 0 as a default value, and then the value, which is the output. So this is here, we don't have input and output. All the variables are in this record, and we handle an in event, init, and that's the variables that basically get new values, and are also the basically what you get in variables basically by the runtime system. The new values are already set here, and we want to get the interval out here. Oh, that's the horizontal overlapping. Yeah, that's the reminder. So I actually triggered that. Interesting. Well spotted, Miriam. So in here we have a state, which is in this case empty. You can have your state here. And then when debounce, a few conditions, and we basically do nothing. We also have a handle info, which is kind of like a normal handle info. Basically, somebody sent us a message. So we got the message fake value with a new value. Sorry. Too much speaking, not enough drinking. So we get our variables here. We get our state, which is empty anyway. We get our function block reference here and a map to the surrounding function blocks, which, never mind. We just need to pass it on. So we get we set the new value in variables, and then when new is 0, we call our helper function PLC function block send out event. We trigger the down event because it went, the new value is down 0, so we send a down event, which is actually wrong here because it needed to be 1 before to actually trigger a down event. But for fake, it's good. It's only for faking it. And then we kind of like send the new variables, and we need to pass this on to this send out event. And that's kind of it. That's how we fake this. And we have a helper function. That's the one I called before. So if you look here, there's mu fake. And all it does is gproc send to the instance. To the instance. So we use gproc to register the instance names locally. And in a distributed case, we actually know we have a static mapping of function blocks to Erlang nodes, and that kind of like then uses the local name at the statically known function thing, and then we send the fake value message basically with gproc send, and that's how this faking goes. So let me show you another one. Oops, that's the wrong. So that's mu in, mu out callback. So that's kind of like the handle in event. We have set on, set off, where we then set the value on, off, and we send the out event, and we kind of like do nothing here. And that's kind of like we want to make a function block like this, which kind of like gets a LED color and then sets the LED. That was the initial plan, but we lost too much time. Okay, I think let's wrap it up here. Or let me show you a few other things. What can I show you in the source code? So kind of like here's the compiler for this whole stuff, but that's, if I start going through here, well, it's I show you the files. It's a parser. It uses a YAC grammar, which is like a YAC grammar for Erlang, so very useful. So you can write a programming language grammar here, and we get basically a parse tree, and then we do stuff to the AST, and in the end we create core Erlang. That's how we create core Erlang. So there's a helper module in core Erlang, which is called CERL core Erlang, which helps you kind of like build core Erlang code. And maybe as a little example for those who didn't hear of core Erlang ever. Core Erlang is a hidden language in the Erlang compiler. So Erlang is a language with quite some interesting scoping rules. So you don't have statically scoping because variables are visible in the whole scope, and you have all kinds of like higher level constructs like list comprehensions and stuff like this. And this gets compiled to a simpler language called core Erlang, which is a very simple functional language with static scope. And it's really simple. And this simple language then goes to the backend, and the backend then basically creates over several stages then optimized beam file from this. And we plug into this, so we actually create this core Erlang files. and then use the backend of the Erlang compiler to actually create beam files out of it. So that was kind of like a very, and then there's a runtime system that helps keep this running. This is actually working. The runtime system, it's working very well. It's controlling a conveyor belt system on 15 network nodes. That's kind of like a research conveyor belt system, like a research factory setup, like 8-meter long only. It's a small factory, but this just works 24/7, and makes sure that everything moves at the conveyor belt correctly. So there's like all kinds of things. Some of you might have seen these videos I show, but I don't have time to show the video now. Come to the conference, look at the video. Okay. Hey Flask, yeah, hour late. Doesn't matter. Replay will be online soon. Not everything worked today as expected, but well, we got it working. Kind of like broke my Erlang installation. Okay, yeah. Checking out now. Dinner time here. Have a nice evening or have a nice day, depending on your time zone. And everybody have a nice weekend. And hope to see some of you on the CodeBeam conference in San Francisco next week, where we actually talk more about this stuff and show hopefully a demo that runs on the GRiSP board, which I didn't build today. Well, homework to do. Okay. Then have a nice weekend. Bye.